example using rotational inertia. So I have a little game set up where I've got 4 objects. They're all going to roll down the same inclined plane. I have a hula hoop, a quarter, racquetball, and a bowling ball. These are all different rotational inertias, different radii, different masses. There's a certain symmetry in how they're going to roll. There's a definite answer for which one is going to reach the bottom first. So let's start off by writing out what the rotational inertia for each of those objects are. So a hula hoop is going to have a rotational inertia that is the mass of the hoop times its radius squared. A quarter, obviously smaller radius and smaller mass, but it's going to have a rotational inertia. In table 8.1 has a prefactor of a half times the mass of the quarter, radius of the quarter squared. A racquetball is hollow inside, so that's going to have a rotational inertia. It goes as 2/3 times the mass of the racquetball times its radius squared. And for the bowling ball, which, except for the holes, unless you got like a really fancy bowling ball with like a liquid core or something super duper, that's like a solid sphere. And that has a rotational inertia. It's going to go as 2/5 mass of the bowling ball times the radius of the bowling ball squared. And then for the hoop, you can imagine it has a prefactor in here as well. It's just 1. And I'm highlighting those prefactors in the formula for the various rotational inertia because that turns out to be key for how energy is going to be shared between kinetic energy of translation and kinetic energy of rotation. So these rotational inertia for things that can roll has a generic form where there's some prefactor beta times the mass of the object times its radius squared. And so what we're saying is for the hoop has beta equal to 1. For a solid disk, beta is equal to a half. For a hollow sphere, it's 2/3. And for a solid sphere, it's 2/5. And that prefactor, the beta value, is telling you something about how much of the mass of the object is along its rotation axis. So if it's a hoop, it's none of it. If it's a bowling ball, then along its rotation axis you have relatively more of its mass. So more of its mass is closer to the rotation axis than is the case for a hollow sphere. And similarly, a solid disk has more of its mass at the rotation axis than a hoop. Alright, so all these objects are going to roll without slipping. So a full rotation of the object takes us through its circumference, and that tells us that its linear speed v is always related to its radius times its angular speed omega. All the objects have a different radius, so they all have like a different diameter, but regardless of that, if you think about it, all of them are going to fall through the same change in height. As they roll down our incline. Okay, so let's write out conservation of energy. So I've got my inclined plane. And some object that can roll is initially at the top, and then in the end, it's at the bottom. So in my initial state, the object is at rest, the top of the incline, and in the final state, it's rolling and at the bottom of the incline, so there won't be any more change in gravitational potential energy. And if we can neglect the work done by non-conservative forces, so like air resistance isn't going to do a significant amount of work, and the work done by non-conservative forces is 0, and the mechanical energy will be conserved. So there is static friction that allows it to roll, but as we've talked about before, for an object that rolls without slipping, that force of static friction isn't able to do any work. The displacement of the wheel or whatever it is that's rolling is perpendicular to the direction of the force of static friction. So the initial mechanical energy will equal the final mechanical energy, assuming it's all starting with gravitational potential energy. At the end, it's all kinetic energy and translation and rotation. So this is a statement that U initial equals U final plus our two kinds of kinetic energy. It's going to be translating as part of its rolling, and it's going to be rotating as part of its rolling. And I'm going to pick the final potential energy to be 0. So that's the point I'm going to measure height from. So this tells us mgh is going to equal a half mv squared plus kinetic energy of rotation is a half I omega squared. And I want to work on this equation for a little bit. I'm going to let all these rolling objects have the same general rotational inertia. So I'm going to substitute in a rotational inertia I of beta mr squared. And we'll have mgh is a half mv squared plus a half beta m r squared omega squared. Now, I have gravitational mass on the left-hand side and inertial mass on the right-hand side. Those are precisely the same. So the mass of the object can't matter. I have one more simplification. And this one might be a little bit more surprising. A half v squared plus a half beta r squared. I'm going to rewrite omega with our rolling without slipping condition. So v over r quantity squared. So actually, the radius of the object doesn't matter either. If it has a larger radius, its circumference it's going to travel in one rotation is larger, but its rotational inertia is larger by that same factor of r. So the mass of the object doesn't matter, and its radius doesn't matter either. So everything had a common factor of 2. I'm going to pull that out to the left-hand side. So I have 2gh is going to equal v squared plus beta v squared, which I can rewrite as speed squared times 1 plus beta. So then I solve for v. V is going to be our familiar answer of 2gh, but now it's divided by 1 plus beta. That's all square root. So let's think about this equation for a little bit. If the object doesn't roll, if it just slides down, then beta is equal to 0, and we have our old friend from kinematics. If there is enough static friction for each of those objects to instead roll, then the larger the value of beta, the slower the linear speed at the bottom. What that means is it has less energy in the kinetic energy of translation, and more of that gravitational potential energy has become rotational kinetic energy. So it's going slower. So the ranking out of our 4 objects is going to be first the bowling ball, because it had a beta of 2/5. The next smallest is actually going to be the quarter. It had a beta of 1/2. Third is going to be the racquetball, because its beta was 2/3. And then last was our hula hoop, because it had the largest beta, 1. So mass of the object doesn't matter, radius of the object doesn't matter, but how the mass in the object is distributed does matter. So if you have more of the mass along the rotation axis, so it makes a smaller contribution to the rotational inertia, it will be quicker rolling down an inclined plane.